Good evening, everyone. This is Algebra 2, Unit 2, Lessons 20, 21, and 22, and we are going to look at solving rational equations today. You're going to notice that the notes will look a little bit different for this one because the notes this time were saved in a Google Slides format. Um, I tried converting it to the system that I normally use to make these recordings, and it just did not look very good at all. So I'm going to try doing them directly on here using Cami and seeing how that turns out. So feel free to let me know if it comes out all right. So I think we're going to do this in two videos. We're going to do lesson 20 now, and then the next video will be lessons 21 and 22 together. 21 is a short one, and I think pairs better with 22 altogether. So we'll make two videos for the three lessons. Okay, so here we go. So our learning targets here that we're going to be looking at, we are going to be writing rational expressions that represent averages to answer questions about a situation. So ultimately, um, we have been looking at the idea of the role of division in um, in life and in just numbers in general. And one of the things that we came up with was the idea of how division makes sort of an inverse relationship between numbers, so that if I have something that's related by division, then as one quantity increases, the other decreases, and vice versa. The example I gave in my last lessons had to do with a birthday party. So you have a cake and you need to divide the cake equally among the people that come. Well, the more people that show up, the smaller each slice of cake has to get. And we looked at the role of big numbers and small numbers and asymptotes. So now we're going to put it together by looking at what can we model by using these rational functions. Ultimately, we'll be creating equations based on them. We'll be looking at ways to cleverly use multiplication and the tools of solving that we already know in order to find the missing values. Unfortunately, one of the things that's going to happen, even if we're doing all the right operations, is we will get, in some cases, answers that may not be truthful. And those come out as a result of the fact that we cannot divide by zero. So if a value has the potential of having a zero in the denominator, we will have to be really careful to kind of recognize when that situation pops up. Okay, so other than that, let's get started. All right, here's a little bit of a warm up for you, just some review things, just so that we remember here. We want to identify all vertical and horizontal asymptotes of these functions. So we'll go through this pretty quickly. I think is fair enough if you've mastered this content already. Even if you haven't, just seeing it again is wonderful. So vertical asymptotes are easy enough, right? So vertical asymptotes are when the denominator equals zero. So I'm just going to put vertical asymptote, okay? Now, hopefully I can write okay with this system. My crosshair is a little bit different, but remember that we want denominators equal to zero. So for some of these functions, like we can tell pretty easily what that's going to be. You know, x equals -2, and x also equals -2 down here. But for this one, remember that when you have something that is quadratic, an expression of this form, we have a quadratic and a linear, you want to maybe factor it, because factoring can tell you where the x-intercepts are. So x breaks down, so x squared breaks down into x and x. -2, what multiplies to -2? Well, it's going to be 2 and 1. And they have to add to get a -1. So that looks like that's going to be -2 and +1. So it factors into x minus 2 and x plus 1. So what are my vertical asymptotes? They're going to exist at x equals 2 and x equals -1. Remember, those are the solutions that make those equal to 0. Now, what about horizontal asymptotes? Now, the lovely part, horizontal asymptotes, there can only be one for a particular function. If it had more than one, we would fail the vertical line test. So for horizontal asymptotes, you don't directly look at the numerator, you look at both of them together. So you're looking to see which is bigger, the numerator or denominator. So for the first function, what's bigger, numerator or denominator? Denominator's bigger, it's got a higher degree, it's got an x squared in it. So what's going to happen when I divide something into bigger and bigger pieces? So as x goes up, x squared is going to get bigger and bigger and bigger and bigger, much bigger than x. So what's going to happen is you're going to get a y of 0 because you're dividing by bigger and bigger and bigger things. So it's like more and more and more people start showing up to the birthday party, so the cake slices are going to tend towards 0. Now, what about this one? In the next case, the numerator is bigger, so x squared's on top, right? So as x increases, the top is going to get bigger and bigger and bigger. Well, this time it's the cake getting bigger and bigger and bigger. So the cake's going to get bigger, much bigger than the number of people. So the slices get bigger and bigger and bigger. So there's no horizontal asymptote. When the numerator is bigger, there's none. For the bottom part, they're equal. These are of equal degree. So what's going to happen in this particular case? As these increase, essentially what's going to happen is the 5 and the 2 just kind of become irrelevant. These numbers get so big that the 5 and the 2 don't really matter. So what you're left with is 7x over x, and you're left with a y value of 7. That would be the horizontal asymptote, because no matter what, if you have, say, a million, you're going to have a number approximately 7 million divided by a number of approximately a million, and so you have 7. So there you go. Easy enough to tell those. So never lose that, because we will use that again from time to time. Okay, so now let's get started with the actual content of the lesson. So, all right, so it looks like we're cut off just a little bit. So let me just put it back. Perfect, there we go. All right, rationalizing the price of t-shirts. So we've had a chance to talk about these averages before, and how we can calculate the average of something. So what is an average? An average is equal to a total given divided by the number of items. So how would you calculate average? It's the sum of everything divided by the number of items. So in this particular case, what we're going to look at here is we're going to look at how that comprehends in terms of t-shirts and costs. So the school art club is in charge of designing t-shirts and getting them printed. A local business charges $35 to set up the machine, $4.25 per t-shirt to print. Okay, fair enough. And so that's true whether we print 1 t-shirt or 1,000 or 1,000,000 of them, right? So let's create an equation to represent cost. Now, if this were Algebra 1, we could find an equation for the cost, right? That's easy. What's the total cost of the t-shirts? The total cost is going to be 25. Sorry, not 25. Wow, 35. Ooh, use my eraser. So 35 plus, now we're going to pay $4.25 for each shirt. And so we're going to use X to represent the shirts. So that's the total cost, right? But it says to create an average cost. And to create the average cost, we divide by the number of items. So what is that in this case? Well, that's just the number of shirts. We divide by the number of shirts. And so this is going to be C of X. All right, next question. What is the average cost per shirt to print 25 shirts or 100 shirts? Okay, easy enough. We just plug those in, right? So let's take a calculator here. Where is calculator? Drag it over. Boop, there we go. So all we have to do is plug 25 in for X, right? So 425 times 25. plus 35 divided by 25, 565. So 425. So for 25 shirts, so I would say C of 25 equals 565. Okay, let's do the same for 100 shirts. 425 times 100, well, that's just 425. We're going to add 35, and then we're going to divide by 100. 460. So it's $4.60 per shirt. Now, here's a good question. Whoops. So C of 100, that's not exactly the way I wanted to write it. Let's go back. Okay. I'll write it a little bit of a more functional format. C of 100 is equal 460. So what does that mean? The more shirts that we purchase, the average price goes down. Again, it's that division concept, right? So essentially, we keep going down and down and down. An average, Bible can save until a point, right? So is there a point where the average just kind of stops? So the cheapest the average cost per t-shirt will get. So we could try to do a little bit of math here. And one way you can think about it is, well, what happens if I buy a zillion t-shirts? But I want you to think about this. Go back up to the function and let's logically think about it. It says local business 35 to set up their t-shirt printing machine. So that's costing money. $4.25 in materials per t-shirt. So if we're already paying $4.25 per t-shirt, can we pay any less than that? No, because we have to then pay an extra $35. So the average cost will approach $4.25, but it will never get there. Although you could make the case that there comes a point where you have like literally fractions of a penny. Like if you made 10,000 t-shirts, um, the average cost would be just slightly over 425. It would be 425 and a fraction of a penny. So there will come a point where the average is essentially that. Okay. However, again, the point remains that the more t-shirts you print, the lower the average cost gets, just up until this point. So notice how at 25 shirts it's 565, and at 100 shirts it's 460. So maybe a question I could ask is, at what point does the average cost reach, say, $5? How many shirts should be printed to have an average cost of $5 or less per shirt? Now, why might this type of question be important? Well, you are the one responsible for making and selling these t-shirts, right? Maybe you're going to sell these t-shirts at a fair or maybe for a class fundraiser, and you want to sell them at a particular price point so that you make profit. Um, Anybody who runs a business will have to do this too. So let's say you want to sell them for $5 each. Well, in order to turn a profit or at least not owe money, we have to print enough of them to get the average down. So can we figure that out? So if you have an average cost of $5, okay, where's that going to go in the function? So it's not X. X represents the number of shirts. We're trying to find X. So instead, what we're trying to do here is plug in C of X. C of X is your average cost. So here's your average cost right here. Oops, I meant to change color there. So C of X is your average cost. That means I can take 5. And I can plug that in for c of x, but then the rest of the function, I can write it out as I had it before, like this. That's kind of a silly looking x. Well, let's do it a little better. Okay, so 5 equals 35 plus 4.25x divided by x. Now, if you had to guess, how many t-shirts do you think that is? So let's see, 565, 460. $5 is kind of somewhere in the middle between there, not perfectly, but kind of in the middle. Um, a little bit closer to 460, so maybe a little bit closer to 100. So let's say, I don't know, 60 maybe. Maybe 60 t-shirts. We know the answer is going to have to be in between the two. So let's see what happens. You can take a guess, but now we can try solving it. Okay, now, I'm not sure if you've solved these equations in Algebra 1, but we could do this here. So think about this. We have an x, but it's in the denominator. Ew. Okay. So this may not look like any equation you've solved before, but let's think. What are your opposite operations? So we have an addition. We have to subtract. We have a multiply by x. For the 4.25x, we'll have to divide by x. But here's the thing. We already have a division by x in the problem. Do the x's just cancel out? No, they don't. You cannot cancel these x's out because the 35 also does not have an x. If 35 had an x, you could cancel all of them out, no problem. So the one thing about x's is if you have a variable, or not just x, but any variable in the denominator, any factor that's there has to divide out of every term in the numerator in order to be able to be removed from the expression. But here we can't. So instead, we have to do opposite operations. So how do you get rid of it dividing by x? We multiply by x. So what I'm going to do is to solve this equation, I have to multiply both sides by x. Now, this seems wild. How do we know what we're multiplying by? Well, we're multiplying by some amount of t-shirts, right? We just don't know what that number is, but we're multiplying by that number. Now, here's the part that you have to be careful of. When you solve an equation like this, you have to have reasonable certainty that x cannot be 0. Kind of like, if you think about a court of law, like, proof beyond a reasonable doubt. So let's think about this logically. In this situation, can x be 0? Well, that would mean no shirts, right? Would we believe that 0 would be an appropriate solution to this problem? No. Selling 0 shirts is going to be nothing because that's just going to cost us $35, and we wouldn't be able to create an average from that. So because we know that x won't be 0, actually, we specifically know that x is in between 25 and 100, we can perform this operation. So I'm going to write a note over here and say, we know x cannot be 0. We know it's in between 25 to 100, based on the work that we've done before. So let's simplify this. Now we have 5x equals 35 plus 4.25x. The idea being that we have now converted to a simple linear equation. And this is the one that, yes, based on your work in Algebra 1 and geometry, I'm sure you could solve it. So subtract 4.25x from both sides. And I get 0.75x equals 35. Oops, I forgot to write it there, but you get the idea. Minus 4.25x. Okay, divide by 0.75. Divide by 0.75. and that'll tell us what x is. So I pull up my calculator. 35 divided by 0.75, 46.6 repeated. Okay, now we can't sell 2/3 of a t-shirt. And we also know that we want to get 5 or less, right? So we know the answer to this, 46.6 repeated. But when we think about it, in order to get the average to go down from 5, we have to go up on the number of t-shirts, right? That inverse relationship. So this is going to end up being 47 t-shirts. Perfect. 47 t-shirts. So, hey, we weren't too far off with 60, but 47 is the right number. And if you go back and plug it in, you can prove it to you, right? So 4.25 times 47, 199.75, add 35, that's 234.75. We're going to divide by 47, 4.9946. And so that is definitely pretty close to 5, but just slightly less. Now, will we make much of a profit at 47 t-shirts? No, we're basically breaking even at that point if we sell them for $5. So we're going to have to make definitely a bit more than 47, but this gives you a nice baseline to figure out what cutoff values that you need. Okay, let's keep going. So that's the kind of problem that we're going to solve with these type of situations. Okay, another good situation that comes up is the idea of a batting average. So Tyler's on a school baseball team. He's had 24 base hits out of 110 at-bats this year. Okay, so what is his current batting average? So batting average, remember average is a record of the total divided by how many things have happened. So in this case, what a batting average is like essentially like a proportion of the number of hits you get out of the number of at-bats. So his batting average is going to be hits divided by at-bats. Now, those of you that know a little bit about baseball know that the idea of an at-bat is different than a plate appearance, and then you have things like walks and hit by pitch and fielder's choice and all this other stuff. There's errors, which don't count as hits, and etc. So we had all this stuff. We're not going to worry about that here. So hits divided by at-bats, his current batting average is 24 out of 110. About 22%, so 0.218. Batting average is always done to 3 decimal places. So we'll do the same thing, 0.218. That is, not great. So, at least not in the major leagues. Now, a school baseball team, maybe, I don't know. But for the major leagues, that's not a good number. Anyway, so we can think about that. And so our friend here decides he wants to work at it. He wants to raise his batting average to 300. And so he's going to concentrate really hard and he's going to get some big hits coming up. And so let's say he goes on a lovely little hot streak. And he gets, every time he comes to the plate, boom, gets a hit. So how many consecutive hits does he need in order to raise his batting average to 300? Ooh, sounds like a lot, doesn't it? Because he's already had 110. If he's already had 110 at bats, right? And he's got to raise his batting average almost 50%. That seems like we're going to need a lot of hits. But let's find out. So how many hits would you predict that he would need? 30, 40? In order to raise it to 300? Let's find out. Okay. So we need to write and solve an equation to represent the situation. Our idea is, what will the equation look like? So let's consider the result of what happens when we get extra hits. So he starts at 24 over 110. What if he gets one extra hit? What would his batting average be? It would be 25 over 111. What if he got two extra hits? His batting average would be 26 out of 112. Why did the denominator increase? Because we're adding plate appearances too. Each time he comes up and gets a hit, that's an extra plate appearance or batting out or at bat and an extra hit. So both numerator and denominator are going to increase. So what about 10? So at 10 extra, what will it be? 34 out of 120. So now our question is, at what point do we get to 300? So we don't know what that number is, right? So let's call it x. So what happens to x? How does the number of hits, extra hits, get worked into the numbers? Well, it's just added to the numerator and denominator, right? So x extra hits is going to be 24 plus x over 110 plus x. We're just simply adding that to the numerator and denominator. So what we want to know is at what point this fraction gets to be 300. So we're going to say 24 plus x over 110 plus x equals 0.300. Now, 0.300 is the same thing as 0.3. So from here on out, I'm just going to write it as 0.3. Okay? All right, let's solve. So in this particular case, again, we want to get rid of the denominator, right? We want to pull x out of the denominator to solve. Now, question, can the denominator be 0 here? That's the one thing we want to try to avoid. In order for the denominator to be 0, x would have to be a negative 110, and we can't have negative extra hits. So we don't have to worry about this ultimately becoming 0. So it's not so much x can't be 0, it's the denominator can't be 0. So I'm going to make a mark over here, and I'm going to say denominator is okay. All right, so let's go ahead and solve. All right, so we're going to multiply both sides, but this time don't just multiply by x, multiply by the whole denominator, okay? So I'm going to multiply everything by 110 plus x. And so the equation that I'm going to have here, that's going to cancel out from the bottom. You're going to have 24 plus x equals 0.3 times 110 plus x. Now, all we have to do is solve this nice linear equation. We're going to distribute. So 33 plus 0.3x. You can prove that to yourself. 110 times 0.3 is 33. And I know that because 11 times 3 is 33. And I just can move the decimal point as much as I need to. So the next numbers to look at are, we want to combine all these like terms, right? You're crossing the equal sign. So we're going to subtract 24 from both sides. And so I get x equals 9 plus 0.3x. Subtract 0.3 from both sides. There we go. So, oops, not negative. That's positive. So 0.7x equals 9. So all we have to do is just divide by 0.7. So x equals 9 divided by 0.7. This one, no, can't do in my head. So 9 divided by zero point 0.7, about 12.86. Actually, I totally did that in my head in class. Don't ask me how, but I did. Now, can we have 0.86 of a hit? No. And we know that 12 is not going to cut it because his batting average keeps going up the more hits he gets. So 12 won't be enough. We're going to go up to 13. Most cases of functions like this, we will round up. Even when the decimals are less than 0.5, you'll see that oftentimes we're going to round up because rounding down will be a situation where we haven't quite reached our goal. So we're going to need 13 hits, probably less than you thought, right? Probably less than you thought. Now go ahead and prove it, right? If you want to check your work, all you simply have to do is plug in the 13 hits. So 24 plus 13 is now 37. And out of 123 total at bats, 0.3008. So that's a batting average of 0.301. And if we tried it at 12, you're not quite there yet, 295. So almost there, but not quite. You just have to go to 13. That's how it works, folks. Okay. So let's do a little bit of practice before we call it a day, shall we? So same idea. Car begins its drive in heavy traffic and continues on the highway without traffic. The average cost of gas this car uses per mile for driving X miles is given as follows. So where do these numbers come from? I would guess here that a car beginning its drive in heavy traffic means it's hardly going anywhere, which means it's almost nothing. And so the 0.65 represents the fact that it costs 65 cents. So it's in dollars. So it's 65 cents just for sitting in traffic because he hasn't gone anywhere. And then once the traffic is gone, maybe they just cleaned up an accident. Then it's 15 cents per mile after that. So what is the average cost of a mile for 10 miles, for 50 miles? Oh, easy, just plug them in, right? Okay. Don't forget, guys, that what you could always do is if you wanted to, you could pause it here, try the question out, and then see how you did in a second. Maybe you could try that. All right, whether or not you paused or continue, that's okay. Let's finish the problem out, right? So for 10 miles, so what's going to happen? Well, let's just use the calculator, right? Oh, did I close it? I closed it. Boop. There we go. Oh, get back here, calculator. Okay, so let's see. 10 miles, right? Well, 0.15 times 10, which I do. 0.215. Average cost of gas per mile. 0.215. So 21.5 cents per mile. But what if you drive 50 miles? The average should go down, right? Because again, we're really in light traffic. We're only paying 15 cents per mile. So after 50 miles, and then we're going to divide by 50. 0.163. Notice how the average has come down after he's driven more miles. And eventually, what number is it going to reach? The cheapest average cost of gas per mile? It will never pass per mile. It'll come close to that, but never reach it. Okay, so that's how it works. Okay. All right. So let's solve now another type of equation here. So let's go back and do another at-bat equation. See if you can do this one, folks. Okay, Jane has 30 base hits out of 92 at bats on her softball team. How many consecutive hits will she need in the game to improve her average to 350? Do you think it's possible that she can accomplish this in just one game? Oh, you know what? Who's got that apostrophe there? That apostrophe should not be there. Bad grammar. Who wrote this stuff? It wasn't me. I never mess up my grammar. Ugh. Okay. Anyway, so do we really have to know what 30 out of 92 is? I suppose we don't. But if you were curious, 30 divided by 92 is 0.326. That part really isn't necessary, except thinking that in one game, that's asking a lot. But let's find out. So when you write the equation, remember, every time you get a hit, all those hits add to the number of hits, and they add to your at-bats. So we get 30 plus x over 92 plus x equals 0.326. Or not 0.326, wow, okay, equals, what target are we trying to get to? 0.350. Okay. So all we have to do is solve that equation. So remember, I'm just kind of going quickly here through this. So 30 plus x, 92 plus x. Can this denominator be 0? No, x would have to be negative. So again, we're good. Let's multiply by 92 plus x. And then all we have to do is distribute and solve. 30 plus x. So I'm not going to write everything completely out. Equals, 0.35 times 92. What is that? 32.2. Okay. All right. I'm running out of room here. Um, we'll just kind of extend down here a little bit. I hope that that's okay because we're getting into the summary part here. Um, mhm. So let's subtract the 30 from both sides. So you get 2.2. Okay. And on this side, we're going to subtract 0.35x from both sides. Let's just write it out. Because I'm running out of, that bar is making me run out of room here. Okay. So subtract the 0.35x from both sides. And then all we have to do is divide. So 2.2 divided by 0.65. 3.38. So x so you can't reach it with 3, you're going to need 4 hits. So, can she accomplish this in one game? Think about what you know about baseball. Can you get 4 hits in a game? Sure, major league players do it all the time. So, I think that's fine. Um, is it possible? Sure. Is it likely? That's another matter. But you could prove it by actually doing the math, right? So if we do 4, so you're adding 4, so that would be 34 divided by 96. Yep, that's 0.354. So imagine that. It looks like it's a pretty fair jump. But that's the lovely part about fractions and how much it increases like that. Okay, so that's really about it for this particular lesson. Just solving some equations based on some simple average situations. The next few lessons are going to be a little bit more just, solving, different kinds of proportional equations based on this. Okay. Um, so here's some more summary stuff if you want to read, kind of have the idea again on how to solve this equation. So Remember, the batting average question, you just stick a plus X onto the fraction to represent the fact that the number of hits, number of at-bats is increasing. And then we solve. We can multiply by the denominator in this case. And if we've done all the way right, we get x being 5 for this particular situation, which you can read on your own. Okay. And so I think we're going to leave it here, folks. So this is lesson 20, and we'll do the next ones last time. So have yourselves a lovely evening and enjoy.